Okay, let's get started. So, today we're going to see some examples or like theorems about how we can use factor groups to understand the larger group that you're given. So let's just recall. So if G is a group and H is a subgroup, we call H normal if for all little g in the group G, we have that the left G coset of H is equal to the right G coset of H. And we also saw last time that if H is normal, then the left H cosets form a group, which is written like G divided by H, and you call this the factor group. Okay, so a lot of times the factor group is simpler than the original group, and so if you're given a group G and you're trying to understand its structure, maybe you want to know what group is this isomorphic to, is it abelian, is it cyclic, things like that, then it might help you to identify normal subgroups and look at the corresponding factor group to figure out some things about your group G. So let's see an example of a theorem, which is like just an example of something you can detect about your group G by looking at a particular factor group. So this is a theorem, and it says that, so let's let G be a group and ZG be the center of G. So those are all of the elements of G that commute with everybody. So we talked about last time, or maybe the time before that, how ZG is an example of a normal subgroup always, because since the elements of ZG commute with everybody, you will always have this condition satisfied. Okay, so ZG is normal inside of G. So we can look at G mod the center, ZG. So if this factor group, G mod ZG, is cyclic, then the group G itself was abelian. Are there questions about the statement? So let's see how to prove this. So let's suppose G mod its center is cyclic. So we'll let G, ZG, so this is some left coset, we're going to let this be a generator. Of G mod ZG. Okay, so then we want to show that G is abelian. So let's take elements A and B in G. And so we want to show that AB is equal to BA. Okay, so how are we going to do this? So let's look at the cosets A, ZG, and B, ZG. So since G mod ZG is cyclic, this is equal to that generator, GZG, to the I for some power I. Okay, and this is just because G mod ZG is cyclic. And of course, this is equal to G to the I ZG. And then we can say the same thing about B. So there exists some J such that this is the generator raised to the jth power. Okay, so then, so this is all, we're looking at the level of G mod ZG. So let's look at what's happening now, what this says about what's going on in G. So this means that A is equal to G to the I times X for some X in the center of G. So why is that? We have on the left-hand side, this is a set, and A is an element of that set. So that means that A must also be an element of this set on the right-hand side. And everything on the right-hand side is of the form G to the I times something in the center of the group. So that means that there is a way to write A as G to the I times something in the center. And similarly, we have a way to write B as G to the J Y for some Y in the center. Okay, so then now we're ready to commute them because what we wanted to do was show that AB is equal to BA. So if we have AB, this is equal to G to the I X, G to the J Y. Okay, and then X and Y commute with everything. So we can rearrange everything as follows. So we can write this as G, J, Y, G, I, X. So this is because X and Y are in the center of G. And then this is, of course, equal to B times A. So that proves that the group G was abelian. Yeah, you have a question?
How do you know you can commute G, J?
Yeah, okay, so these are just powers of one element G, right? So I can, if I is bigger than J, I'll leave behind J copies of G here, commute everything over, and yeah, so, yeah, everything that's written here commutes with each other because the Y's and the X's are in the center and the G's are just copies of G. Is there another, I think I saw another hand. Do you have a question?
Why is G, V, G, I equal to G, I?
Okay, so the question was, why is this equality? Why does this hold? This is by definition of multiplication of cosets. So like when we saw what is the group structure for cosets, yeah, if you have like Yeah, so I'll just write a little more here. So let's say I took GZG times GZG. This is equal to G squared ZG, just by how we define the multiplication in this group. Yeah. Other questions? Yeah.
Wait, sorry. Can you go back in why you know that A equals G to the I of X?
Yeah. Okay, so the question is, why do we have A is equal to G to the IX? So let's look at these two sets, which we're saying are equal. So A is an element of this one on the left-hand side because the identity is in ZG. Right, so A is in here, which means that A must also be in this set. But everything in this set is written as G to the IX. So that means that A is equal to some G to the IX. Yeah. Okay, good. Other questions? Okay, let me make a little bit of commentary about this theorem. So it said if G mod ZG is cyclic, then G is abelian. But if G is abelian, then actually ZG is equal to G. So this was actually just the trivial group, the group only containing the identity. So that's like one observation. So if you ever like encounter a situation where this is cyclic, it actually is just the identity. And then the other observation is just that if G is not abelian, then automatically you know that this is not cyclic. So those are just some other things that you can deduce from this statement. Okay, so we know that ZG is always normal in G. So this may lead us to ask the question of what is G mod ZG in general. And we actually can answer this question. So the next theorem that I'm going to give you is going to be a way or a group that this is isomorphic to. But before we do that, I have to introduce a definition. So when we talked about isomorphisms, we also talked a little bit about automorphisms, so isomorphisms from a group to itself. And this is going to be a specific type of automorphism. So I'm going to let G be a group. And then I'll let A be an element of G. Then we have a function that I'm going to write as phi sub A that goes from the group G to itself. And what it does is it sends an element little g to A, G, A inverse. And this is called the inner automorphism of G induced by A. And the set of all inner automorphisms is called in G. So let me just say some facts about these, and I'll give you a few minutes to think about these, think about why they're true, and discuss together. So the first claimed fact is that the inner automorphisms are in fact automorphisms. So they give bijections from G to G, and they preserve the operation. The second claimed fact is that in G is a group under composition. And then I guess the third thing, which is follows from the first two, is that in G is a subgroup of aught G, which is all of the automorphisms of G. Okay, so I'm going to give you a few minutes to think about these and discuss. Yeah, did you have a question?
It's about the previous video.
Yeah.
When you said that if G is abelian, then G over ZG would be the identity. Do you mean like it would be just G, or do you mean just be the element E?
It would just be the element E. So if G is abelian, then the center, ZG, is all of G. So this is equal to G. So then G mod ZG, this is like G mod G, so this would just be the identity. Yeah. Okay, so I'm going to give you a few minutes to think about these facts about inner automorphisms, and we won't prove these because hopefully like showing these kinds of things is like getting routine at this point, but then after that we'll discuss how this relates to factor groups. Okay, let's go ahead and see how this relates to factor groups. So we have the following theorem. So this says for any group G, we have that G mod ZG is isomorphic to in G. Okay, so let's see how to prove this. So to prove that these two things are isomorphic, what we need to do is find a candidate isomorphism. So we have to find a candidate isomorphism. And then typically when you define something on a factor group, you also have to show that it's well defined. So that will happen here. We'll have to show our map is well defined. And then the last thing that we'll do is we'll prove that it's an isomorphism. So we'll show injective, surjective, and operation preserving. Okay, so let's start off with this, the candidate isomorphism. So let's consider the map from G mod ZG to in G given by, so if we have a coset GZG, we're going to send that to the corresponding inner automorphism phi sub G. Okay, I think that's like probably the most natural thing, the thing that makes the most sense, simply because in this case, like, we constructed elements of in G just to correspond to elements of G. So the thing that makes the most sense given an element of G is to just make the corresponding inner automorphism. Okay, so let's see why this is well defined. So that means that we need to show that if GZG is equal to HZG, then my map actually does the same thing to both representations of this. So we have phi G is equal to phi H. So that's what we're going to show here. So let's suppose GZG is equal to HZG. Then that means, like by coset properties that we had, that H inverse G is an element of ZG. So this is by properties of cosets. So that means that for all X in G, so I'm just translating what it means that H inverse G is in the center of G. For all X in G, we have that this element H inverse G X that these two things commute. So this is equal to x h inverse g. But then multiplying both sides on the right by g inverse and both sides on the left by h, I get that this is equal to gx g inverse is equal to hx h inverse. And that statement holds for all x and g. So that means that phi g is equal to phi h. Okay, are there questions up to this point? Yeah.
Is using the small g, is that different from using the big G? For the first line?
Sorry, where are you?
Well, this line, the first line. G, Z, G small.
Oh, yeah, sorry, these should be big G's. Sorry about that. Okay, other questions? Okay, so let's continue. So we found a candidate isomorphism and we showed that it was well defined. So now we have to do injective, surjective, and operation preserving. Injective is essentially going to be reversing the argument that we just did. So let's see why that's the case. So let's suppose that I have phi g equal to phi h. I have two outputs of my map and we're supposing that they're the same, so we need to show that the inputs were the same. So that means that gx g inverse is equal to hx h inverse for all x in g. And then rearranging this equation, that then tells me that h inverse gx is equal to x h inverse g. And so that tells me that h inverse g commutes with all x's. So h inverse g is in the center of g. And by the coset properties, this implies that gzg is equal to hzg. Okay, so we've just reversed the argument above to see that our correspondence is injective. Surjective comes very easily. So this is basically by construction. So if phi g is an element of ng, because all elements of ng have this form, then the coset that maps to it is the one gzg. Okay, so now we know that our correspondence is injective and surjective. So the last thing that we have to show is that it's operation preserving. Okay, so for that, I am going to make a name for the map. So I'm going to say T is the map from G mod ZG to NG, where T of GZG is equal to phi G. Okay, so now my isomorphism has a name, and it is T. Okay, so we need to see that when I apply this to the product of two elements, this is the same as individually applying T to those elements and then multiplying them. So I'm going to look at T of GZG times HZG. Okay, so I have like two elements that I'm taking the product of and then applying T. And we want to see that this is equal to T of GZG times T of HZG. Okay, and so this is going to get even a little bit more complicated. So this object, what is this? This is an element of in G, so that means that it's a map from G to G. So I need to look at what this map does to an element X in G. So I'm going to let little x be an element of G. Okay, does it make sense? So let's compute what this map does to X. Okay, so by the definition of multiplication in factor groups, this is equal to T, GH, ZG of X. Okay, and then T of GHZG, this is the inner automorphism phi sub GH, and we'll apply that to X. So what is this inner automorphism? I do GH X, and then I have to invert, so we'll do GH inverse. This is GH X H inverse G inverse. Okay, so now I can see, I'm just going to look, I'm just going to look first at this like inner portion. So this is G phi HX G inverse. Okay, and then what is this? This is applying phi G to phi H of X. So really we're just kind of like unpacking the definition and notations here. So there's like a lot of layers, so it could get confusing, but I think just going step by step, you won't make any mistakes or mess anything up. So phi G is of course T of GZG, and we are, so that is some inner automorphism. We're applying that to the element phi H of X, and then phi H of X is, so I have T, G, ZG, and then phi H is T, H, ZG, and I'm applying all of this to the element X. Okay, so we finally have gotten to the end of this. So that shows that my map is operation preserving, and that completes the proof of this isomorphism. Yeah, question?
Yeah, can you explain why like that whole T object is acting on X, but also like T is acting on GCG times HCG? Like, can you explain the difference?
Just like explain this
Yeah.
this notation. Okay, so T is a map from this factor group to in G. So whatever the output of T is, that is itself a map from G to G. So like, so let me write this as an aside. So let's say I have T and I apply it to some element of the factor group. This is a map from G to G. So I can like ask, what is this map do to an element X in G? Yeah. And then this is like, okay, now instead of putting in just one element GZG, I'm putting in the product of two elements. Does that make sense? Okay. Yeah.
Can you go back to the bottom? I don't understand how the very last step works. How do you get, how do you end up like multiplying the two t's? Oh, because it's composition.
So the operation is composition. So I could have done this in two steps. I could have written this first as THZG and then observed that composition was the operation. So that's what this multiplication is. Yeah. Other questions? Okay, I'll make a comment that like, as you continue on in math, calculations like this will come up where you have like a lot of different objects at play and a lot of different types of objects, and you have to just like keep track of where does everything live, what type of object is it, and what are the rules of how I can work with this object. So this is like a good type of calculation or proof to just become comfortable with, because like stuff like this does come up like a lot as you continue on in math. Okay, so I wanted to talk about one final sort of application of factor groups to seeing what you can learn about a group from factor groups. So I'm going to give you one more theorem for today, and this one is called Cauchy's theorem for abelian groups, and it says the following. So we're going to let G be a finite abelian group, and we'll let P be a prime that divides the order of the group G. Then this theorem says that G has an element of order P. So I'll just pause for a second and just sort of like observe that we had for cyclic groups like this really powerful theorem that said for every divisor of the order of the group, you had a unique subgroup of that order, and then it tells you also like how to count how many elements there are of each of those orders. So for cyclic groups, like you can really determine everything, but then as soon as you start to like relax the conditions on the group, so now we're just working in an abelian group, suddenly like it becomes a lot harder even just to guarantee that you have elements of prime order for the primes that divide the order of the group. So I think of this theorem as sort of like fitting into that sort of class of like what happens if we relax some of the assumptions in the fundamental theorem of cyclic groups, like what can you then say? Okay, so this proof is by strong induction on the order of the group. Okay, so for the base case, let's suppose that the order of G is equal to 2. Okay, so then the statement is saying we want a prime that divides 2, and we want to guarantee that the group has an element of that prime order. The only prime in this case is 2, and so we just need to show that G has an element of order 2, which of course is true because if you have a group of order 2, there's one element that's the identity, there's one element that's not the identity, and that element has to have order 2. So the non-identity element of G has order 2. So that proves the theorem for the base case. Okay, so then for the induction step, we're going to have the following inductive hypothesis. So we're going to assume that for all groups with order smaller than the order of G, that this statement is true. So for all groups with order smaller than the order of G, if P divides the order of that group, I should just give these, so I'm going to say for all groups H with order smaller than G, if P divides the order of H, then H has an element of order P. Sorry? Yeah, so this should also be a prime. So if P prime, yes, okay, so this is our inductive hypothesis. So what we're going to do is look at a factor group, then apply the inductive hypothesis to the factor group, so we'll get an element of order P in the factor group, and then show or use that element to construct an element in the larger group that also has order P. Okay, to do this, first, I claim that G just has some element of prime order. For some prime, not my favorite prime P, but just that there is an element of prime order. So to see this, let's suppose X is in G and the order of X is equal to M. where m is equal to q times n for some prime q. Okay, so we can always write this, if I take any element x in G, it has some order. As long as x is not the identity, there will be a prime number that divides its order. So I can write this. Then the element x to the n has order q. Okay, so I know that G has elements with some prime order. So let's let x be an element of G with prime order Q. Okay, if Q is equal to my favorite prime number, P, then I'm done. If Q is not equal to P, then I'm going to look at the group G prime, which is G mod the subgroup generated by X. Okay, and I can do this because this is a normal subgroup because I'm in an abelian group. So when you're in an abelian group, all subgroups are normal. Okay, so then I can apply my inductive hypothesis to G prime. So G prime has an element of order P. By the way, why does P divide the order of G? The order of G prime. The order of G prime is equal to the order of G divided by the order of X, which was equal to Q, and Q is not equal to P. So since P divides the order of G, it will also divide the order of G prime. Okay, we are unfortunately out of time, so we are one sentence away from finishing this proof, but we'll have to save that for next time. So, oh, hey. So next time we'll see how to use this element to get an element of G that has order P. How's it going? Yeah. Yeah. Everyone starts standing up and he just starts barking. Hey, Ian.
a great day.
You too.
Lonely